All right, so now let's work on the secant graph. So in this equation, again, we're looking at the identifying the period first. So, and again, the period just like cosine and just like cosecant, and it's just going to be 2 pi over b, which in this case, even though our b is negative, again, period is representing a distance. It's not going to be positive or negative, so therefore we're just going to leave this as 2 pi over 1, which is just 2 pi. All right. Now we can see we're multiplying by negative on the inside, so therefore we were going to have a reflection about the y-axis, and we have a subtraction outside of the function, so therefore that's going to be a vertical transformation down 2. Now it's important as far as the secant graph, what we've talked about, what we looked at is, when you have a reflection inside of the graph, which we haven't discussed yet before, that is not going to be affecting the asymptotes. Just like actually when we had a reflection about the y-axis, like when I reflect this graph about the x or the y-axis, like, for instance, if I'm looking here, like that doesn't change where the asymptotes occur, right? The same thing occurs with the reflection about the y-axis. When I'm reflecting these about the y-axis, my asymptotes are not going to change, nor does a reflection about the y-axis change the range. So we are going to include them or talk about them, and I'm doing what my students are doing by writing -2 instead of writing -2 or 2 units down. So 2 units down. All right. But anyways, I just wanted to kind of explain that because we can work on this a couple different ways. But when we start talking about the range and the asymptotes, I want to kind of like explain a little bit where we're getting some of these points. So anyways, let's go ahead and just kind of take a look at what this graph would look like. So by looking at the cosine graph, because now we're using the reciprocal of secant, which is the cosine graph. And if you remember on the parent function here, that graph, put it in 2 pi. Say that's pi. So then the graph would look something like this, right? Close enough. That's 1 and -1. So we can see here, we don't have any stretch or compression. The graph is being reflected about the y-axis. And one thing that we learned about the y-axis, or at least about the cosine graph, is if you reflect this graph about the y-axis, what you notice is you're going to get the exact same graph. And the reason being is because this graph is even. So it's actually not going to be affecting this graph at all. Like a reflection about the y-axis is going to provide you the same graph. The only difference here now is we have this graph being shifted 2 units down. So if I wanted to shift this graph 2 units down, I guess I couldn't work that. So let's just delete that. So now to shift this graph 2 units down, now instead of the graph, it's down 2. Jeez. So I need to go, so down 2. So 2. Okay. So now this is going to be kind of like my new intercept. And sometimes I'll draw like a little dotted line to represent the x-axis just so I can kind of get a good sketch of my graph. So again, each point that was originally on that graph is being shifted down 2. So this point would be now up here. So the graph is going to look something like this. Something like this. Now, obviously, my period has not changed, so we're still going to be at the 2 pi region. But again, our purpose here is not to draw the cosine graph, but to draw the secant graph. But again, I'm just using the cosine graph so we can have a better understanding of where these intercepts, where the asymptotes in the graph is going to look like. And again, since these intercept, doesn't matter if it's being shifted down, the original graph here without no period change, right? There was no stretching or compressing that changed the asymptotes. I'm still going to have my asymptotes at a pi halves and at a 3 pi halves. And that is basically from the parent function that we looked at. And therefore now I can sketch the graph going in these directions. That's at pi. There to there, and then this graph will be going from there. Okay, so now based on this information, it makes it a lot easier for me to identify the range. So the range, as I can see it, is going to be from -infinity all the way up to, let's see, that's -1, -2, that's -3. So I'm going to write, not included. You want to use parentheses. So that'd be -infinity to -3. That's included though. Union. And then we're going to go from -1 to infinity. Okay. Now the asymptotes is where I wanted to kind of make that distinction about the reflection not checking. And that's one thing that, again, if you want to use Desmos, you can play around with that. Check this link and you can go ahead and use the negative or non-negative. You're going to see the asymptotes are not going to change. And the reason why I mention this is because when we need to find the vertical asymptotes, as we mentioned before, we're going to take whatever transformations we're doing inside of the function, and we're going to set that equal to our asymptotes. Now, for cosecant, the equation of our asymptotes was pi n. But for secant, our equation of our asymptotes, so when I had, y equals secant of x, that's with no transformations, our asymptotes take on the equation x equals pi halves plus pi n. And again, that's from the parent function that we talked about previously. You can see that the asymptotes occur at pi halves plus pi n. But if we have a different transformation inside of the function, then we can rewrite it. Well, in this case, we don't really actually have any transformation that's going to change our asymptotes. We just have a reflection. And we can look at that again. We can still double check that. X, negative x, so you take whatever's inside your function, set it equal to pi halves plus pi n. And it kind of gets a little confusing, but if you divide it by -1, you would get x is going to equal to a negative pi halves minus pi n. And you say, well, that is technically different than what answer you gave over there. And yes, you are correct. However, if you plug in values in for n, positive and negative integers, you're still going to get pi over 2. You're still going to get 3 pi over 2. You're going to get all the same asymptotes. So actually, these are equivalent equations here for the equation of the asymptote. So even though this is a correct answer on a quiz, I would give the students credit for it. On a multiple choice exam, you're more likely to receive, you're going to see this as a more simplified of a solution than this one. And it's just important that you can understand the differences between those two. So that's really the kind of point I wanted to make with that. But anyway, since we now know our asymptote, we can go ahead and say our domain is going to be all real numbers such that x cannot equal, I'll use the simplified version, pi halves plus pi n. All right, so now let's move on to the next one, where you can see now in this case we have our graph is going to be horizontally compressed, and then we also have some interesting operations here. So again, in the spirit of writing this with the b factored out times x minus c, I'm going to rewrite this equation. So by rewriting this, first of all, I'm going to rewrite this as fractions instead of division. I don't know where the 2 came from. And hopefully you see that 1/3 x plus 1/3 pi is the same thing as x over 3 and pi over 3, right? But now it's a little bit easier for me to see, oh, I can factor out that 1/3. So therefore, this would look like 1/3 times an x plus pi. And again, if you wanted to check your work, just multiply it back over here. But now when it's in this format, I can understand what's going on. I can understand my A, my B, and my C, and my D if I had one, but in this case, I don't. So we don't need to worry about D. But that's why it's so important to put it in this format rather than this one where the B and the C are kind of hard to identify unless you know what you're looking for. So again, A is really not going to be doing too much for us as far as, an answer for secant, but it is going to help us identify the range because that is going to affect the range of secant. So let's go and look at the period. So the period here is my B. So remember the period for secant is going to be 2 pi divided by 1/3. And that is going to equal 6 pi. Multiplied by the reciprocal. We have a phase shift now. You can see that the graph is being shifted pi units to the left, not pi over 3 to the left. So therefore, we can say left pi over 3. And that is really our only transformations. Obviously, we have a horizontal, let's say that's a horizontal compression as well as a vertical compression as well as a horizontal stretch that's happening. So we have both those operations that are being applied. So this one's going to be kind of interesting to see what's happening here. But the important thing is understanding that, if we're just looking at the asymptotes at x equals pi halves plus pi n, they're going to change, right? As far as do I have anything over here in this equation? Yeah, so this one. See, in this one, you can see that my my range is affected by the 1/2. But my asymptotes are affected by what's inside of the function. And that's the important thing of understanding the difference between operations outside compared to inside of the function. So let's try to get like a rough sketch here of cosine in terms of cosine. So that would be 1/2 cosine of 1/3 times x plus pi. Now, again, when you have the benefit of graphing, doing a rough sketch, and you can make your own scale. So I know this graph is going to be shifted pi units to the left, right? And again, remember the cosine starts at 0. So if you're shifting it pi units to the left, the initial period is now going to start at negative pi. So I'm just going to say that's my starting point. And I know that based on the 1/2, that's going to be my amplitude. And with no vertical transformations, this graph is going to go as high as 1/2 and as down as 1/2. Now, the next thing is we know the period. This graph is going to take 6 pi to repeat itself. So we know half of that, which would be 3 pi. And you're not always going to know the x scale, or x scale is easy, and sometimes you have to figure it out. Remember, just the x scale in our notes is just take the period divided by 4, and you can see the distance between all of these coordinate points. But anyways, now let's kind of look at where the asymptotes occur, or what this graph is going to do. Now, I can actually figure this out from the graph. I can figure out that half of 3 pi is going to be where my asymptote. Actually, that's not half of 3 pi. That's 6. Negative pi to 6 pi. That's wrong. Got to be careful there. That's actually 7 pi, right? Because we went to negative 1 pi. That's at negative. That's not 0. So that's not 3 pi. So I made a mistake. So don't do that. Be careful. So let's figure out. We'll actually mathematically figure that out. Don't want to assume things. But we do know. We do have our height here, right? So we know that the graph, and we do know where the asymptotes occur. We just don't know where these asymptotes are. But we're going to figure it out. I was just being lazy and starting to assume or trying to make some connections there. Okay, so here's our graph. Based on this kind of sketch graph, I can now understand my range. I know my range is going to be from negative infinity to the lower point of my cosine graph, which is negative 1/2. And then union, it's going to be from 1/2 to infinity. All right. And now to figure out where these asymptotes are. So again, we got to understand what happened. The original period of cosine was from 0 to 2 pi. And then it got stretched all the way to 6 pi, as well as got shifted pi units to the left. So the period got expanded, and then the graph got moved over. That's a lot of things that are happening. So what we're going to do is we're going to set this equal, whatever's inside of our function, equal to our equation. Now, there's a couple different ways you could do this. We could say x over 3 plus pi over 3 equals pi halves plus pi n. That's the equation of the asymptote for secant. But this looks like it's a lot of fractions to me. So I don't really like that idea. So why don't we try, actually I'll just rewrite it. Why don't we try using our factored out form? So this would be 1/3 times x plus pi equals pi halves plus pi n. So it doesn't matter which form you use. One might be easier mathematically than the other, and we'll kind of see. So the first thing that I'm going to do here is to get rid of the 1/3. So I need to multiply by 3 on both sides. Just make sure you distribute that 3 to both of them. And in that case, then I'm going to be left with x plus pi is equal to 3 pi halves plus pi n. And now I just need to subtract pi. So again, when subtracting pi, you can rewrite that in terms of 2 as a negative 2 pi over 2. And again, you can't subtract it from the pi n because those are not like terms. So therefore, I would get x is equal to, that's going to be pi halves plus pi n. And cool, look at that. It gives you actually the exact same asymptote. So by looking at in recording the 1/3, so by expanding it, now I'm going to have to check that. That's the 1/3, so it's really being multiplied by 1/3, but then also shifting back to the 3. So that's 6 pi. Oh, I forgot to distribute the 3. Oh, geez, man. That's a 3n, right? There you go. 3 pi n. I was like, that doesn't seem right. How do you get the exact same asymptote? So that's going to be plus 3 pi n. There you go. So now my domain is going to be all real numbers such that x cannot equal pi halves plus 3 pi n. Okay. All right. So now let's go and look into this last one here for secant. Again, we're going to have a vertical stretch. And then we have a b here. Now, again, this might be easier to look at like this. 3 equals secant of 2/3 x. So you can see that my b here is 2/3, but I don't have a phase shift, nor do I have a vertical shift up and down. So my period is really just going to be 2 pi over 2/3 multiplied by the reciprocal, 3/2 times 3/2, and I get 6 divided by 2, which equals 3 pi. No vertical transformation, no phase shift. We know there's a vertical stretch here, and there's also going to be a horizontal stretch. So let's just go and take a look at what the cosine graph would look like, so we can identify the domain and range. So the graph is 3. If I'm going to draft cosine, if I'm going to draft this in terms of cosine, I'm going to go up to 3, down to 3, right? And I'm going to complete a period in terms of 3 pi. So that graph is going to look something like this. Now, again, I'm not going to make the mistake as I did last time and try to figure out where these x-intercepts are, right? You can do that. All you got to do is take the period, divide it by 4, and you can figure out those x-intercepts. But we could also do it just by using the equation of the asymptote, Now, I know that the graph here has asymptotes there, and there's going to take this form. So I'm going to draw that just so I can visually see the range. And by doing that, I can see that my range here is going to be from -infinity to -3, included, union 3 to infinity. All right. Now the domain, again, I need to figure out where these asymptotes are. So all I'm going to simply do is, again, take what transformations I have inside of my function, which is 2/3 x, and set that equal to my equation for my asymptotes for secant. And then I'm just going to multiply by the reciprocal on both sides. So 3 over 2 on the left side and 3 over 2 on the right side. And now when doing that, I get x is equal to, let's see, that's going to be 3 pi over 4 plus 3 pi over 2n. And we could probably simplify that. Yeah, maybe one more time simplify that, but I'll just kind of go with that answer for right now. So therefore, our domain, these are my asymptotes. For my domain that's going to be all real numbers such that x cannot equal 3 pi over 4 plus 3 pi over 2n. Okay. There you go. And now let's go ahead, and that is for the secant. Hopefully that kind of helped you guys out as far as understanding the asymptotes as well as the range. And again, I'm not a big proponent of being able to graph, but I think understanding at least what the reciprocal graph is doing as far as its graphing helps you better understand what what your reciprocal function is going to look like. So now let's go ahead and move away from the reciprocal functions of cosine and secant, and let's get on to some cotangent problems.